So going back to the original, I write 4x cubed times e to the power u, because 2x to the fourth is what I decided u would be. And then instead of writing dx, I'll write 1 over 8x cubed du. So I replaced 2x to the fourth with u, and I replaced dx with 1 over 8x cubed du. So I see this x cubed over here cancels with that x cubed. And 4 divided by 8 is just 1/2. So I can rewrite this as 1/2 times the antiderivative of e to the u du, which is going to give me 1/2. And what's the antiderivative of e to the u? Yep, just plain old e to the u. Don't forget r plus c. And then I reverse my substitution. I say that this has to be 1/2 e to the power 2x to the fourth plus c. So this is my answer in terms of x. It's always good to return your answer back into your original variable, like x. Don't leave it as the u's. Still give you partial credit if you leave it as the u's, because I find I make that mistake a lot if I don't have a reason to remember it. Okay, so that was question 1. In question 2, what should be my u choice? Okay. 2t to the fourth minus 8t. So now I take the derivative of u with respect to t. What's that derivative?
8t to the 3 minus 8.
Okay. So I need to rearrange and solve for dt so I can replace that dt. So I multiply both sides by dt, and I'm going to divide both sides by 8t cubed minus 8. And so I have that formula. So going back to the original, in the numerator I still have t cubed minus 1 divided by u to the power 3/2
times,
and yeah, and then
times 1 over 8t3 minus 8
yep,
times du.
perfect. Okay. What's going on over here in this denominator is that there's an 8 greatest common factor there. So if I factor out the 8, it'll look like t cubed minus 1 over here divided by u to the 3/2 power times 1 divided by 8 times, and then after factoring out the 8, I get t cubed minus 1. So now I say this t cubed minus 1 factor in the numerator and this t cubed minus 1 factor in the denominator can cancel. I can bring out the 1 over 8, and that becomes 1 over 8. And I'm left with the antiderivative of 1 divided by u to the 3/2 power. But since we have a u to the 3/2 in the denominator, I could instead move that up to the numerator and call it u to the negative 3/2. Because that's how negative exponents work. And my antiderivative power rule says I'm going to add plus 1 to the exponent. And so plus 1 to the exponent would make that u to the negative 1/2 power. And then I divide by my new exponent. And dividing by negative half is like the same thing as multiplying by a negative 2. And then I still have to divide by 8. I can't forget that, and I can't forget my plus c. Negative 2 over 8 is negative 1/4. And u to the power negative half is just square root of u. And then the last thing I have to do is replace u with 2t to the 4th minus 8t. So this is going to be square root 2t to the 4th minus 8t, all plus c. That one was a more difficult question, a little bit more challenging. Several things you needed to remember from algebra there. Mostly just remember how negative exponents work. If you have a u to the 3/2 power, but it's in the denominator, that's the same thing as a u to the negative 3/2 power in the numerator. And then when you have u to the negative 1/2 power in the numerator, that's the same thing as u to the half power in the denominator, which is the same thing as square root u in the denominator. Any questions about that one?
For the negative 3 over 2,
Mm-hmm.
you subtracted one or you added one?
I added one. Yeah. So it's important to keep the derivative power rule and the antiderivative power rule straight in your head, right? Because in the derivative power rule, we reduce the exponent by 1. We subtract 1 from our exponent. And then we multiply the whole thing times the old exponent. In the antiderivative power rule, we add 1 to the exponent, which is opposite. And then we divide by the new exponent, which is also opposite. So the antiderivative power rule is opposite the derivative power rule in like every way, which should make sense. If we wanted to check our work and make sure we got our answer right, since this was such a long question, all we have to do is take the derivative of our answer and see if we get back our original integrand. So if I take this and I take the derivative with respect to t, I'm gonna rewrite this a little bit to make it easier to take my derivative. Because all of this junk is in the denominator, I can rewrite that in the numerator just using a negative exponent, right? So I still keep the negative 1/4, but then where this is a square root, that's going to be like the half power, and since it's in the denominator, it's going to be like the negative half power. So this is going to be 2t to the 4th minus 8t to the negative half power plus c. And I haven't taken the derivative yet, but what I need to do is then take the derivative with respect to t of all of this junk. And when I take the derivative, I reduce the exponent by 1, or I subtract 1 away from the exponent. So that becomes a negative 3/2 power instead of negative 1/2. I keep the negative 1/4 around, and then the inside is 2t to the 4th minus 8t. And then the derivative chain rule says I now have to multiply times whatever is going on inside the parentheses here. So the derivative of this stuff would be 8t cubed minus 8. So just rearranging this a little bit more, I keep the negative 1/4. This 8t cubed minus 8 goes into the numerator, and then all that stuff with the negative 3/2 power goes into the denominator. So I write 2t to the 4th minus 8t to the power 3/2. And let's see if that checks out. 2t to the 4th minus 8t to the power 3/2. And Let's see. It looks like I've made a mistake, but I can't tell where. So I should have 2.
Oh, you just
I need to
distribute the 4 on the bottom, and then you divide. Oh no.
Mm-hmm.
The 8t. So or you take out the 8 on the top, I think. Right?
Yeah, so I should factor out the 8 on the top.
Yeah.
Yeah, and I don't have any more room, so I'll just have to rearrange this like that with my eraser. But it would be like 8t cubed minus 1 on the top. And I do have a t cubed minus 1 on the top over here. And then I have the 4, which is like 8 over 4, which is 2. So I could divide 8 by 4 and just write a 2. And so it gives me negative 2 t cubed minus 1 over all that stuff. But my problem is that that negative 2 isn't in my original, it's not in my original integrand. So my question is, where did I mess up here? I took the derivative here, and the derivative power rule says I reduced that by 1. Oh, and then I forgot the other part of the derivative power rule, which is you multiply by original. So if I multiplied by the negative 1/2 here, that would be important. So where it says negative 1/4, I also need to multiply by a negative 1/2. I didn't leave myself enough room here. But this is negative 1/4 times negative 1/2. So negative 1/4 times negative 1/2 is positive 1 over 8. And really, again, what I was missing at this step was multiplying by a negative 1/2. So if I multiply the negative 2 times a negative 1/2, that makes it a positive 1, so that goes away. So I did, and in fact, if I take my derivative correctly, I do get back my original integrand.
Or even if you just
So
have
it checks.
8t cubed minus 8, and you had the 1/8 factored out, it'd still be over 8, so you could just divide it by 8 and still work out.
Yeah. Yep. Exactly. So if you're on an exam and you have to do a long antiderivative problem, you want to check your work, make sure you got it right. Try taking the derivative of your answer and see if you get back the original integrand. But I guess maybe the lesson learned here is if you take the derivative and it doesn't perfectly match your integrand, maybe you made a mistake with the antiderivative, maybe you made a mistake while checking your work, taking the derivative, right? So anyways, not to confuse you, but both skills are important. Okay, any last questions about this quiz? And we'll move on to today. Today we're doing something that I think is a little bit more challenging. This might be one of the most challenging concepts that we're going to learn this semester. And it's called integration by parts. And what we do in integration by parts is just another antiderivative method. Whereas if you have an antiderivative, you can't just do it immediately because it doesn't follow the power rule or the exponent rule or the reciprocal rule. And you can't solve it by U substitution because there are some antiderivatives where U substitution doesn't work. Then we can use what we call integration by parts. And it's going to seem really, really strange. You just kind of have to get used to it, right? It's not going to seem like it's very straightforward. But anyways, here's what our procedure is going to look like. You are going to split your integrand. Remember, your integrand is what you're trying to take the antiderivative of. Split it into just two parts. Take one part to be the first part and one part to be the second part. Hence, integration by parts. And then I like to sketch out a little blank table where my first column just has alternating positive and negative signs. So I have a positive and then a negative and then a positive and then a negative and then so on. As many as you need. In the first column, we're going to write the first part down. And then we're going to write the derivative of that first part. And then we're going to write the second derivative of the first part below that. And then we're going to write the third derivative of the first part below that. And we're going to keep taking derivatives, more and more and more derivatives, as many as we need to take in that second column. And then in the third column of my table here, I'm going to take the second part and write that right here. And then I'm going to take the antiderivative of the second part and write that below that. And then I'm going to take the second antiderivative of the second part and write it below that. And then I'm going to take the third antiderivative of the second part and write it below that. And I keep going as many times as I need to go. But by splitting up my integrand into two different parts, it's going to make it easier to take that antiderivative. So taking the antiderivative of just the second part should be easier than taking the antiderivative of the whole integrand. And then once we've filled out our table, we're going to sort of pair things up in a diagonal way. So you're going to start off for your first two columns on the first row, and then you're going to jump down to the second row for the third column. And you just continue to pair stuff up like that. Like I said, this is weird. I know it doesn't make any sense. Just got to get used to it. And then at the end, when we've multiplied everything with these little snake patterns, we're going to have a bunch of terms. In this case, I've drawn 3 different terms. We're going to add up those 3 terms, and that's going to be your antiderivative in the end. So without further ado, let's do an example. I have the antiderivative of x squared times e to the x with respect to x. So my integrand is x squared times e to the x. So I might say that x squared is going to be my first part, and that e to the x can be my second part. Okay. So then we would make a table, and the first thing, and it's very important, is that you write a couple of alternating plus and minus signs, like plus, minus, plus, minus. Next to the plus sign, I'm going to write my first part, which is x squared. Next to that, in the third column of my little table, I write my second part, which is e to the x. Okay, all good so far? So then in the second column with the x squared, we're going to take derivatives. The first derivative is
2x.
Perfect. What's my second derivative?
2.
2. And what's the third derivative?
0.
0. And if you get a 0, then that's good. You've gone far enough if you end up with a 0. So this is going to be enough for us. What's the antiderivative of e to the x? E to the x, and we can ignore the plus c for now. And then the antiderivative of that would be e to the x, and the antiderivative of that would be e to the x. So this is my table.
So wait, so there's no plus c's in this?
Yeah, we're ignoring the plus c's for now. At the very end, when we write our antiderivative, we'll add a little plus c. But for right now, we're good. Then what I'm going to do is sort of pair things up with the little snaky pattern where I actually drop down one row to grab my third column, like this. And so I'm pairing things up like so. Everything that's inside each one of these little orange snakes is going to multiply, and then I'm going to add my 3 orange snakes together. And this antiderivative, my answer to this problem is going to be this: plus x squared e to the x minus 2x e to the x plus 2 e to the x, and then plus c. So that's integration by parts.
That's it?
Mm-hmm.
That's it?
That's it. So these problems are a little bit trickier if you wanted to check your work. So like if I were like, yeah, I don't really trust myself, let me check to make sure that this antiderivative really is the derivative. The reason it's a little bit difficult to check is because you have to remember your derivative product rule, because like this first term, x squared e to the x, is a product of two functions. So my derivative product rule, ignoring that one for now, we'll come back to it. My derivative product rule here would say, well, f prime g plus f g prime, and then my derivative product rule here would say minus 2 times f prime g minus 2 times f g prime. And then I don't need to use the product rule for that one. I just use plus 2, and then derivative of e to the x is e to the x, and the derivative of constant is constant. Now, what's going to cancel from this derivative? Well, I have 2x e to the x, and I have a negative 2x e to the x. So these two are going to cancel out. I have a minus 2 e to the x and a plus 2 e to the x, so those two are going to cancel out. And so what I'm left with is x squared e to the x, and that's actually my integrand that I started with. So taking the derivative of my antiderivative does check out. It seems like we did this problem correctly. So, any questions about this first integration by parts problem? Okay. Stop me and let me know if you aren't following one of our little steps here. But yeah, if you do take the derivative, it should always work out, regardless of what type of antiderivative problem it is. Okay, so moving on to our second one here. I have antiderivative of t times e to the t. Noticing that we can't solve it by u substitution, I'm going to draw my little table, plus, minus, plus, minus. In my second column, I'm going to write t. And in my third column, I'll write e to the t. And so what's the derivative of t? 1. And what's the derivative of 1?
0.
Okay, so I'm good there. E to the t, what's the antiderivative?
E to the t.
And then antiderivative of e to the t is e to the t. And that's as far as I need to go. So this one's a little bit shorter. I'm going to connect up my snakes like this. And this. This time I only have 2 terms. And this answer gives me plus t e to the t minus e to the t plus c. That should be your antiderivative. This should work if you take your derivative.
Wouldn't you add another? Is it because there's a 0? And then if you would have connected with another e to the t, it wouldn't be.
Yeah. Yeah, you're right. If we had kept going, then 0 times e to the t would still be 0. So it doesn't matter. And once you get to your first 0, that's where you can stop your table. That's a good question. So we're going to skip the natural log part for just right now. Just going to ignore that. Well, maybe. I don't want to confuse you, and I can't remember if this is tricky or not, but we're going to try this. Whenever I see natural log of x dx, or the antiderivative of natural log x with respect to x, you might think about it like this. You might think about it like natural log of x times 1 with respect to x, because after all, if you multiply something times 1, it doesn't really change it. So then my first part is going to be this natural log, and when I go to write my table, I'll write plus minus, I'll write natural log x. And then my second part is just going to be the number 1. And what's the derivative of natural log?
1 over x.
Perfect, 1 over x. What is the antiderivative of 1? X. Perfect. It is x. Now we're going to just stop the table right here. And like I said, I don't want to confuse you. Hopefully this is going to make sense. If not, I think I can clear it up later. But we're going to write one little snake that goes like this, the way we would normally write the snake with, moving down one row in the last column. And then we're going to write another snake, but this snake is going to look a little bit strange because we're going to write a perfectly horizontal snake. And when I go to write this out, I'm going to write x times natural log x plus x natural log x. So I write x times natural log of x. And then for this little horizontal snake, I have minus 1 over x times x. So x divided by x is just 1. So this is like a minus 1. But if you choose to terminate your problem at a horizontal snake, you have to write the antiderivative. So we're going to take the minus antiderivative of 1. And I know that sounds ridiculous. It sounds like I'm just making stuff up today. There is a reason why we're doing this. You're going to find out that it does work in the end. We're going to check our answer. But I know it just sounds silly, but this is the way that I remember how this works. So I'm going to write, again, x times natural log of x. And then what would be the antiderivative of 1? Well, we just talked about this. Clarissa said, yeah, it was just x. So I'll write x natural log x minus x, and then don't forget plus c. So what if we check our answer and we take the derivative of this? Well, derivative product rule here, because I have x times natural log x, tells me f prime g plus f g prime, and then the derivative of minus x would just be minus 1. Derivative of a constant is 0. So then x times 1 over x is just 1, so I could write natural log x plus 1 minus 1, and then plus 1 minus 1 cancels out, so I just have natural log of x. And that is my original integrand. So taking the derivative of that antiderivative does work. So while it may sound like I'm just totally making shit up with the droopy snakes and the horizontal snakes, there's a reason why I'm doing it, and like I said, maybe I'll sort of show you why. Like, how did mathematicians figure this out in the first place? Why did they start making little tables with the snakes and everything? There is a method to it. So before we move on, questions about antiderivative natural log?
This horizontal snake rule only applies to logs?
It could apply to anything,
Yeah.
but it's useful in this case because we do have a logarithm.
Okay.
Yeah. So.
Sorry, so it would apply like if you know how the last time we had our 3 and it ended at 0. Let's say it wasn't a 0. Could you still do that horizontally? We can run that.
Yeah. So let me show you what it would look like if we rewound the clock and we went back here and we said, instead of doing that diagonal snake, we choose to terminate our table with just this horizontal snake, like here. I do this instead. Let's see what that would look like. So in our previous example, we have plus t times e to the t, so t e to the t, and then I'll switch my pen color to blue for my horizontal snake. And what I said, the trick about horizontal snakes is you have to actually write antiderivative of. So I have minus 1 times e to the t, so this is minus 1 times antiderivative e to the t, dt. And so then this would be t e to the t. What's the antiderivative of e to the t? Well, it's still e to the t, and then I write a plus c. So like it still works,
Just take an extra step.
Yeah.
with the antiderivative.
Yeah. And you don't have to write this down, but one other thing I can point out here is that if I had kept going with the table, we might be interested in what happens, right? If I, instead of just writing a little horizontal snake and ending it right there, what would have happened if I had kept going with this table for my natural log example? Right here.
It would have.
So I'm going to erase this little purple check. Hopefully we know how to take derivatives. And then I'm going to keep the same problem. I'm going to extend my table down an extra row. So I have plus natural log x, 1, minus 1 over x, x. Then I have plus, I have to take the derivative of 1 over x. So that's like the derivative of x to the negative 1 power. So I bring down the negative 1 and I make that negative 1 power into a negative 2 power for my next derivative. And then for the antiderivative of x, I add 1 to the exponent, so that becomes x squared, and I divide by my new exponent like this. So now, like I said, if I just started doing this, and I decide to do 2 diagonal snakes with just 1 horizontal snake at the end, but this time I'm adding 3 terms together instead of 2, like the original way I solved it. I'm saying that this should still work for me. So let me write plus x natural log x. Now minus 1 divided by x times half times x squared, and then now plus negative x to the negative 2 power times 1/2 times x to the 2 power plus c. Well, whenever I have x to the negative 2 power times x to the 2 power, that's like x squared divided by x squared, so those are going to pretty much cancel each other out. Whenever I have, oh crap, and I forgot one other thing. Ha. I forgot that whenever I do a horizontal snake, I have to write antiderivative of, like this, for that term that came from the horizontal snake. Okay, it really feels like I'm making stuff up now. Then over here, whenever I have x squared divided by x, that's just x. It's like x times x divided by x. And so that's going to be, in the end, x times natural log x minus half x. And then I have plus the antiderivative of negative half. And the antiderivative of negative half with respect to x is just negative half x plus c. So minus half x is the same thing as minus 1x. And so in the end, I have x natural log x minus x plus c. And that's what I got originally. So it turns out with the natural log table, the way we set it up, you can make as many rows as you want, and you can do as many diagonal little snakes as you want. In the end, to put a period and finish our problem, we have to terminate this with a horizontal snake. We can't just keep going forever in our table. But no matter where you decide to leave off, whether you leave off of after 1 or 2 or 3, you always get the same answer. So again, hopefully each of these little explanations is clarifying and not just confusing you more. That's what every teacher dreams of. Okay, so let's try this next one then. The one that I just, whoops, cancel. This next one says antiderivative of t times natural log of t. So I'm going to make my little table again. This time I'm going to let my first part be natural log of x and my second part be t. Oh, yeah, you're right. Thank you. Natural log of t on my first part. So in my first part, I'm going to take the derivative of natural log. And the derivative of natural log is 1 over t, or I could write t to the negative 1 power if I want to. I take that derivative. And then I'll take, what's the antiderivative of just t? Hmm?
Oh, antiderivative.
Yeah.
Negative
t squared.
negative t and negative 2 on the top.
So I'm going to add 1 to the exponent. Instead of having t to the 1 power, I'll have t to the 2 power. And then I divide by my new exponent. So that's the antiderivative of just t is 1/2 t squared. Okay. Now, just like I did before in the previous problem, I'm going to link up these guys and then link together these guys. So with the red grouping, that gives me plus 1/2 t squared natural log t. So I have 1/2 t squared natural log of t. And then with my second grouping, let's see if it works. I have minus, and then since it's horizontal completely, I have to say antiderivative. Minus antiderivative of t to the negative 1 power times t squared. And so t squared times t to the negative 1 is just t. You can think of it as like t squared divided by t is just t. So this is going to be minus 1/2 of t. And I take the antiderivative of that term with respect to t. So here's 1/2 t squared, natural log t, and this is minus 1/2. The antiderivative of t, we just solved that, it was 1/2 t squared plus c. And I'm curious about whether or not this will work if we decide to check by taking the derivative. So my derivative power rule for the first term says this is going to be 1/2 of f prime g, so 2t natural log t, plus 1/2 f g prime t squared times 1 over t, minus 1/2 times 1/2 is 1/4, and then my derivative power rule says that t squared is going to become times 2t, and the derivative of the constant is 0. So let's see, can I cancel anything out? Maybe, maybe not. So here, in this middle term, I have 1/2 t squared divided by t. Well, t squared divided by t is just t, so that middle term is really just 1/2 t. This 2 in the numerator and this 4 in the denominator can sort of cancel and give me 1/2 t. So I have plus 1/2 t minus 1/2 t, so I don't have to worry about either of those last two terms. They cancel it out. And then 1/2 times 2, well, 1/2 of 2 is just 1, so that cancels out. And so when I check by taking my derivative, I get t natural log t, which is my original integrand. So that checks out. After taking the derivative of my antiderivative, I get what I started with. That's the way it should happen. So anyways, that works out. I guess moving on to the next example. Antiderivative of x cubed e to the 2x. So we make a little table, plus, minus, plus, minus. And in the first column, let me just choose my first part to be e to the 2x and my second part to be x cubed. So then if I take the derivative of e to the 2x several times, I'm going to get 2e to the 2x, then 4e to the 2x, and then 8e to the 2x. By the way, don't write this. Just wait one moment, sorry. Don't write this because I'm about to show you how this is a huge mistake. The antiderivative of x cubed would be 1/4 x to the 4th, and the antiderivative of 1/4 x to the 4th would be 1/20th x to the 5th, and the antiderivative of that would be 1/100th x to the 6th, and so on. But on the right side, I just keep going up in powers. Like I go 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12, and you know that numbers keep going. And on this middle column, I still have e to the 2x every time, so that middle column's not going away. The crappy thing is that if I were to then try to make these columns super duper long, and infinitely long, honestly, and then pair them up like this, I would end up with infinitely many terms. That's not good. And if I were to try to just stop at some point and take like one of these horizontal groupings, remember the trick with the horizontal grouping is that you have to end up taking the antiderivative of that. And this antiderivative is even more difficult than the antiderivative I started with. So this is a problem, and I made it a problem because I chose the wrong first part and the wrong second part. So the correct way to solve this is to make my first part x cubed and my second part e to the 2x. So let me repeat, my first part has to be x cubed and my second part has to be e to the 2x. So now when I take derivatives of x cubed, you can start writing in your notes because this is going to be the right solution. The derivative of x cubed is 3x squared. The derivative of 3x squared is 6x. The derivative of 6x is 6, and the derivative of 6 would be 0. So actually, one of my columns terminated with a 0, so that's good. It didn't go on for infinity. It actually stopped. And ideally, when you're solving a math problem on an exam, you want the problem to stop. You don't want it to continue for the rest of time. On the side with the e to the 2x, the antiderivative of e to the 2x is going to be half e to the 2x. The antiderivative of half e to the 2x will be 1/4 e to the 2x. The antiderivative of 1/4 e to the 2x will be 1/8 e to the 2x. And the antiderivative of that will be 1/16 e to the 2x.
So for the first column, it's always the derivative, and then the other one is the antiderivative.
Yeah, that middle column is always the derivative, and the right column is always the antiderivative. But it matters, like I've just pointed out, it really matters which part of the integrand goes in which one. Yeah, you want your middle column, after taking derivatives, to eventually go to 0. At least for the case when you have an exponential. In the case where you had the natural log, it turns out you always want the natural log to be in the middle column, and your t's or your x's to go in the right column. And whenever you have the exponential function, you want your t's or your x's to go in the middle column, and you want your exponential function to go in the right column. So those are basically the two cases of integration by parts that we're going to do in this class.
Okay, so why would you have the log on the right? Like what makes the difference? You know, like having the log on the right side of the...
Oh, you're saying what would happen if we did the logarithm on the right side?
Yeah. Well, yeah. Yeah.
Okay. Yeah, let's try that. I'm going to write this below it. So I'll choose new color. And so if I had the same table but the logarithm was on the right and t was in the middle, what would happen? So the t goes to 0 eventually. That's good when I take derivatives. Antiderivative of natural log t is... you don't necessarily have that memorized off the top of your head, but maybe you did memorize it, right? Maybe you saw this problem and you said, I'm going to memorize that antiderivative. So the antiderivative of natural log of t would be t times natural log t minus t. What's the antiderivative of t times natural log t minus t? Yeah.
So
It's difficult. Yeah. In order to take the antiderivative of t natural log t, you would actually have had to solve this problem already. But we're actually trying to solve that problem. So in order to solve the problem, you would have had to already solve the problem. and that's a problem. Okay, good question though. I like these questions. It's interesting to mess around. And it's also important to see what it looks like to make the wrong choice, because if you are working on an exam and you make the wrong choice on an exam and you start to work the problem, it's good to be able to recognize, ah, man, I need to flip those two and restart, because it's nice to know what it looks like so that you can, maybe not waste too much time going down the wrong path. So anyways, I've made my little table. If I want to find my antiderivative, I just have to pair up all these terms like this, kind of diagonal way. And I can stop after this one because the next one would contain 0, and 0 times anything is still 0. So to write out my answer, I'm going to have plus half times x cubed times e to the 2x minus 3/4 x squared e to the 2x plus 6/8, and 6/8 is just 3/4 x e to the 2x, and then also minus 6/16, which is 3/8 e to the 2x, and then plus c. So that's my antiderivative. And we won't check this answer because it has so many terms I'll get bored. All right. So we have just a few more minutes left in class. We've got 17 minutes. Let's, I don't know if anyone here actually cares, but in case you did care, I'll try to explain why this works. And so we're going to start with the derivative product rule. And the derivative product rule told us that if I have the product of two functions, f times g, and I'm trying to take the derivative of that product, my answer was f prime g plus f g prime. Another way I could write this is by writing the derivative, we'll say with respect to x, of f times g. That would be equal to the derivative of f with respect to x times g plus f times the derivative of g with respect to x. Because you know the g prime just means the derivative of g. Then what I'll do is on the left side of this equation, I'm going to take let me just start a new line because I wrote everything too close together. I'm going to take the antiderivative of the derivative of f times g. And on the right side, I have to take the antiderivative of the derivative of f with respect to x times g plus the antiderivative of f times the derivative of g with respect to x, like this. And this equation is still balanced because I did the same thing to both sides. On the left side I took the antiderivative, on the right side I took the antiderivative, so we're all good. On the left, the antiderivative with respect to x of the derivative with respect to x of f times g is just f times g. And on the right side, what I have is that let me think about this. What I have is that the derivative of the antiderivative of the derivative of f with respect to x times g plus the antiderivative of f times the derivative of g with respect to x is I mean, these are equal to each other, basically. So what we're doing, well, let me make one more step here. I'm gonna subtract this last thing from both sides of the equation. So on the left side, I'll have f times g minus antiderivative of f times dg dx dx. And on the right side, I have derivative of f with respect to x times g dx. I'll just change this because multiplication is commutative, so I can also write this as g times df dx, like that. So, in fact, let me do one last thing, and it's not important. You don't have to write this, but I'm just going to change it so that the right side and the left side of the equation are just swapped. So I'm still saying that this is equal to this minus that. And the idea that we've done is we've said we are going to choose a first part. And then we're going to choose a second part. And the first part that we've chosen is essentially this g inside this antiderivative. And the second part that we've chosen is essentially this df dx inside the antiderivative. Okay? And so in my little table, where I'd write plus minus, my first part would be g, and my second part would be df dx. And taking the derivative of g would be dg dx, and taking the antiderivative of this would give me f. Okay? The way that we paired things up inside this table when we were ready to write our solution was sort of diagonally. So we would write plus f times g as the first term that we wrote out. And then I told you that if you want to, you could terminate the whole thing just by writing a horizontal section, but then you would have to take the antiderivative if you want to end with a horizontal. So that's like writing minus the antiderivative of f times dg dx with respect to x, which is like that term right here. But if you decide to keep going with this little table, what ends up happening is that you're basically saying, I need to solve this by integration by parts. And so you apply the same formula again, but you're starting now with this as your new first part, and this one as your new second part. And when you write another line of this table, you're basically saying, I'm taking, no, sorry, my bad. I got my first and my seconds confused. That's the new first part, and that's the new second part. There we go. Because when you write another line of this table, the new first part is going to have the derivative, sorry, the second derivative of that g, and the new second part is actually going to be the antiderivative of f. So you start taking antiderivatives going in the third column, and you take derivatives going in the second column. And the reason that this little table works is because this formula happens to work. And each time you create a new line in your table, it's like you're executing that formula again for the antiderivative you have yet to solve for. And the reason that this whole formula works is because you can start from our derivative product rule, and you can just sort of take antiderivatives and rearrange it a bunch, and then you can eventually get to this formula. One little thing, and then we'll go back to doing examples. And the little thing is that a lot of times you see this integration by parts formula. You might see it written like this. So like if you ever choose to use any kind of online resource to help you with this class, and you're like watching a YouTube video or reading some article on the internet, you'll probably see this described as the integration by parts formula. Again, the reason for this is because they are talking about they're talking about this as being dv, and they're talking about this as being u. So they're saying our first part that we've been talking about is lowercase u, and our second part that we've been talking about is what they call dv. And so then we write f times g, that would be like v times u, or u times v, and we write minus antiderivative of f, but that would be the same thing as v, and the derivative of g would be the same thing as the derivative of u, or du. So you could write antiderivative of v du, and so that's why you see this thing going on. Again, if this doesn't help you, you don't have to remember this. What's important for this class is that you're just able to calculate and use this formula, which is, again, going back to our little table schematics like this one. As long as you can do this, that's all you need to know. I like to mention these explanations in case students are interested in seeing why does this work. I want to prove to you that I'm not just making shit up in this class, that there's actually a basis for it. Okay. I guess 8 minutes left. Let's try to do a few more. So here I have another natural log problem. Like I said about natural logs, you always want the natural log to go in the middle, and you want your t's to go on the right if you have a t times the natural log kind of integrand. So the derivative of natural log 2t is going to be 1 over t. The derivative of 1 over t is going to be like the derivative of t to the negative 1 power, which is like negative t to the negative 2 power. Then I'm taking antiderivatives of t squared. So antiderivatives of t squared would be like 1/3 t cube. And then the second antiderivative would be 1 over 12 t to the 4th. And maybe this is all we need. Yeah, in fact, we didn't even need this third row. That was just for fun, I guess. So then I'm going to pair up these terms. And then, after I pair up those terms, I'll pair up these horizontal group of terms. Remembering that if I do a horizontal, then I have to take the antiderivative of that. So my little terms that I filled out in the diagonal are plus 1/3 t cube natural log 2t. And then in my little diagonal terms, or sorry, my horizontal terms, I have minus 1/3, and then I have to take antiderivative. And then t cubed divided by t is just t squared. So I write that. 1/3 t cubed natural log 2t. The antiderivative of t squared is going to raise the exponent from 2 to 3, and then I divide by my new exponent so that 1/3 becomes a 1/9. And then don't forget your plus c. I don't know if you guys have noticed this, because I think it's really strange that you know that the natural log of t, when I take the derivative, that is 1 over t. But whenever I take the derivative of natural log times 1 trillion, times t, that's also 1 over t. In fact, the derivative of natural log of anything times t is just 1 over t. And so it almost feels like you're like awkwardly losing information because this k could have been any number, and after you take the derivative, you don't really know what it was. And that's kind of weird. Again, the reason that this works is the derivative chain rule, because if I'm taking the derivative of natural log of some number k times t, well, I think the derivative of natural log is 1 over whatever goes inside the natural log, so it should be 1 over kt. But then the chain rule, the derivative chain rule, says now I have to multiply times the derivative of my inside function. If my inside function is kt, then that derivative must be k. And then, well, I have a k in the numerator and a k in the denominator, and so the k's cancel, my derivative is always 1 over t. So then you think, well, here's a problem, because if I take the antiderivative of the derivative of anything, I should be able to get back my thing I started with, right? And if I take the antiderivative of the derivative of natural log x and the antiderivative of the derivative of, like, let's say 5 natural log 5x, well then how am I going to end up with natural log x in this case and natural log 5x in this case? Well, hopefully this is going to be a very quick explainer. The derivative of natural log x is going to be 1 over x. The antiderivative of 1 over x is natural log x plus c. The derivative of natural log 5x is going to be 1 over x. And the antiderivative of 1 over x is natural log x plus c. So it almost looks like you lost the 5, right? You had a natural log 5x here, and if you take the antiderivative of the derivative of natural log 5x, you just get natural log x plus c. But if I show you y equals natural log 5x and y equals natural log x plus c, and you're allowed to choose what the value of c should be, then we can always choose a value of c that makes natural log x plus c the same as natural log 5x. So the only difference between natural log x and natural log 5x is just a vertical translation, which can actually happen with the right choice of c. So it's not, to me, the first time I saw that, I was like, man, that really feels like a contradiction. It feels like math just got broken. But no, the trick is the flexibility in the plus c. Any last questions? Got 1 minute. All right. Like I said, U-subs, they definitely take practice if you're going to do well on your exam. You've got to practice those U-substitution antiderivatives. Same thing for integration by parts. If you want to do well in the exam, you've got to practice your integration by parts. Something that it's just not going to happen naturally.